Hey everyone, welcome back. This is Star, and now I will go over the rest of the runtime analysis in this worksheet. And this time I will go it a little bit faster because we already get a general idea of how it looks like to do this kind of analysis. All right, so for the second question, we still have an input n. All right, and in the first line of code, we have a if statement, and we say if n is smaller than 1, we're going to directly return. And this will serve as a base case for our recursive function, because as we see here, we are doing recursion, or this is a recursive function. All right. So after the base case, we see there is a for loop, and it is a for loop from I equals to 0 to I is less than n. And therefore, we're going to run this for loop n times. And inside each time, or like when we run this loop each time, we're going to do a work that is linear 100. However, remember we said before that linear runs in linear time with respect to the input. What does that mean? That means the larger input is, the larger this is going to be. However, in this case, the input is always 100. It is always 100. Therefore, this part, or this specific function, will run in theta 100 instead of theta n, because you are giving it a constant input. It will run in constant time. And as we said before, constant does not matter. So this is the same asymptotically, the same as theta 1. That being said, we are doing a theta 1 work inside this for loop, and we're doing this for loop n times. So in conclusion, this part, the for loop in general, will give us a theta n runtime. All right? So it will run in linear time. And after that, we're going to have two recursive call and cut the input size in half. So what does that mean? I always find it is really good to draw out a tree structure so that to help you to analyze the runtime of a recursion function. So I will see how that goes. I will erase this and hopefully get more space. And then so I will draw it here. So in this case, originally we have an input n. All right? And in each case, or in each function call, we're going to split it into two sub-functions, or two recursive functions. Each of this recursive function will have an input size of n over 2. All right? And therefore, for our next part, it will be n over 4. N over 4. So we'll have 4 terms with input n over 4. We're going to keep doing this until we reach, we're going to keep doing this until we reach the base case where our input size is just 1, and we can return from it directly. All right. So first we want to see how many nodes are there. So the number of nodes. So how many nodes are there? So first, in order to find that, we can first find how many layers are there. All right. And the reason why that finding the number of layers is better than finding the number of nodes is because it's much easier. Because at first, we start with a size n, and then we divide it by 2 every time it reaches 1. So how many layers are there? And by some algebra, we can find that there is log 2n layers. All right? And in each layer, since we want to find the total runtime, which is like the total amount of work we are doing, so we want to find the number of work per layer, if that's possible. And it is possible because we will first look at how many works were done per node. So the first one, we are said for all the function calls, the only thing that is taking extra work, or that is giving us amount of work, is this for loop. And this for loop will be run in a linear runtime with respect to this input. On that being said, the first part, or the first layer will give us a theta n runtime. And the second layer, for each node, it will give us a theta n over 2 runtime. All right, and there are two of it. So in total, there are two of it, and the runtime is both theta n over 2. So in total, this layer will give us, again, theta n runtime. And we can see the same thing is here. For in the third layer, each node is giving us theta n over 4, and there is 4 nodes. So in the third layer, there is, again, theta n runtime. All right, so we know the work per layer is a linear, so theta n. And then we want to know the total work. So what is the total work? The total work will just be the work per layer times the number of the layers. So therefore, the total work will just be theta n times log 2n, which again, as we said before, the term here for the logarithm does not matter for any constant. So we can write it as theta n log n. All right? And that's the answer for this question. And the reason why we can use theta here is, again, there is no best case or worst case, because we cannot assume the size of n. And as n goes to infinity, we're going to run this for loop no matter what. So yeah, that's for this question.